prediction of seizure types, and identification of seizure onset zones. Some of you know about epilepsy. In fact, like epilepsy is characterized by recurrent seizures or fits. So, from the EEG signals and signal processing methods, we would like to answer the following questions. When one will get seizure? If he or she, let's say, is getting seizures, whether will it be going to means it will be going to accompany with clinical manifestations or not? If it is if it is with clinical manifestations, let's say, whether will it be life threatening or not? So those questions we are planning to those informations, let's say, we are going to extract from the EEG signals. Then recently we start working on facial EMG signals. In fact, we are interested in exploring the applicability of facial EMG signals for the myelotry control purpose. Means this will be very helpful for particularly people those who have like complete loss of let's say all the four limbs, called tetraplegics. Then if you look at the first two topics, the first topic is muscle, and then the second topic is means first topic is about muscles, and then the second topic is about brain. We are also interested in analyzing the communications between the brain and muscle in various movements. And like we are also interested in seeing how this communication differs in normals and abnormals. So we strongly believe that such kind of understanding will help us to develop an active rehabilitation tool for the neurological disorders, particularly such like specifically we say in stroke. Okay, so in this lecture, I would like to give a brief introduction on biosignals, and then I'll talk about different types of biosignals, and then why we have to process these biosignals, and then I'll discuss some of our research works that we conducted on detection of muscle fatigue conditions and then epilepsy. So coming to signals, so what is signal? Signal is nothing but it's a function of independent variable. In most of the cases, as far as signal processing is concerned and biomedical, signal processing field is concerned, okay, signal is function of time. But this independent variable can be like frequency. Let's say we have signal, time domain signal, we apply Fourier transform. It's a simple technique to determine the frequency components of the signals. Then what we will get is we will get a spectral information. So that spectral information, the spectrum is nothing but it's a signal with frequency as independent variable, right? So this independent variable can be time, or can be frequency, or can be space. So biosignals, it gives quantitative and qualitative information about the physiological mechanisms of living system. For example, like ECG, let me take, it's a biomedical signal. It's a typical biomedical signal. I just know, I think most of you may have known this. ECG, it gives information about the heart functions, and EEG, it gives information about electroencephalography, it gives information about the brain functions. So this signal carries information about the physiology, carries information about the functional state of human body. Here you see, like I have shown ECG signals. It's a normal normal ECG, but it is corrupted by some noise, high frequency noise. Okay. Whereas in another case, this is a normal EEG. You can see, for example, if you process the signal, you can extract the clean ECG from this noisy ECG signal. Here we have shown another signal. It's abnormal ECG signal, because this peak says that there is something wrong in the what are the biosignals? Biosignals does not mean only electrical signals. Need not have to be only electrical signals. It could be mechanical, means it could be mechanical activity or it could be magnetic activity. So we have different biosignals. For example, EEG, let's say electroencephalography, as I said, it gives it's electrical activity of brain. EOG, let's say it's EOG electroocculogram, so it provides information about eye movements, electrical activity of eye movements, and EMG, let's say electrical activity of muscles, muscle contractions. So these are like electrical activity. Similarly, we also have mechanical activities. For example, intracorneal pressure. I've shown this here. Intracorneal pressure or blood pressure, or let's say heart sounds. Those are all mechanical activities. Grayocardiography. It's a new non-invasive technique that measures the heart motions using gyroscope. So it's a mechanical activity. So we have electrical activity. Biosignals, we have electrical activity. It could be electrical activity, or it could be mechanical activity, or it could be magnetic activity, magnetoencephalogram. In fact, this MEG plays a vital role in determining, in localizing the epileptic brain tissue. Okay, epileptic brain tissue. So it provides a complementary information than the conventional EEG techniques, EEG and iris vision EEG techniques. Then we also have EHG, okay, EHG electrohistogram or uterine EMG. Okay, electrohistogram is nothing but an electrical activity of uterine muscles. The other name of EHG is uterine EMG. We also have fetal EMG and tachodynamometer, and EMG is, as I said, it's muscles. Okay, it gives information about muscular contraction, give information about motions, movements. So accelerometer is again another example for mechanical signals. So we have different biomedical signals. So now, what are the components of biomedical devices? Okay, biomedical device. So if you take any device in general, biomedical device, have these three components. The first one is signal acquisition hardware. The signal acquisition hardware consists of transducers, amplifiers, and then some conversion. So, for example, now a lot of research are going on. A lot of research are happening towards developing a transducer, particularly for wearable devices, because this transducers, or let's say electrodes, has to be as small as possible, so that the patients can be comfortably wear, and they can use it for monitoring. Okay, and this signal acquisition hardware also has to be the signal acquisition hardware should have a capability of monitoring the signals for a long-term conditions, So these are some of the research components associated with signal acquisition hardwares. Then there comes signal processing framework. Then the first and foremost process, once we record the signal, first and foremost process, what we do is we try to remove the noises. Okay, first we have to know what are the possible noises. Then we have to remove this. We have to remove the noises. And when we intend to remove the noises, we have to be very careful. Okay, we should not remove the desired information. Okay, we should not remove the desired information, because we are talking about biomedical signals. So signals associated with the human body. So ultimately, it will be used for the detection and prediction purpose. So if we remove some desired information, then it may lead to some wrong, some unfair, decisions. Okay. And then we also have event detections. Event detection, for some case, we have event detection. For example, let's say we are interested in monitoring the muscle activity. Yes, in that case, we have some unit, okay, that detects the onset of muscle activity. The same, let's say, for EEG, if you are interested in measuring EEG activity, in that case, we are not interested in event detection. Okay, then we also have some signal processing components. It could be for example, it could be some decompositions, it could be some sort of processing. Then means like no, these are like no, usually done to extract some reliable features, right? No, because like no, the what actually the signal which we record, we cannot directly use it for diagnosis or prediction or detection. Okay, we have to convert the signal, okay, into meaningful form. Okay, meaningful form in the sense, I mean, like from that, like we means from the signal, like we have to detect or predict the actual physiological condition. So, like we have to identify reliable biomarkers using some signal processing techniques. Then, this using these features, what like we will have like pattern recognition algorithms or some misleading models, some detection models, some prediction models can be used to model those variations so that like this can be used in real time life. So now, what are the issues? Let's say, if you look at noise, we categorize this noise into four different types. Uh, means like we categorize into like low frequency and high frequency noise. Low frequency, the example of low frequency is motion artifacts, and high frequency, the example is power line interferences and crosstalk from other sources. We also categorize this noise in another way, namely physiological and non-physiological. Means physiological noises means noise that arises from the human body itself. For example, let's say when we record EEG signals, like some of you may aware about EEG signals, and like because like and you also may aware about 1020 electrode systems. So whenever we record EEGs, okay, EEGs from scalp electrodes, definitely we also have the signals from facial muscles and the signals from eye muscles. So this is something which we don't want. It is not going to give any information to the brain. So this, but like we cannot avoid. We cannot avoid. This will be recorded because it's there in the system. Right? So these are all physiological noises. In another case, non-physiological noise. Non-physiological noise, we can say instrumentation noise. Instrumentation noise is one example, and then some like movement artifacts. Movement artifacts is like it comes under like non-physiological artifacts. Okay, for example, like when we record signals, particularly like this, we will observe in when we record SEMG signals, surface electromyography signals in dynamic contractions. Because like for example, when we place electrodes, let's say in calf muscles, like when we place electrodes and we ask them to, let's say, like run or like they do some activity, then there will be some movement of muscles. This movement of muscles, when the muscle moves, then there are also some disturbance in the electrode that will again like create some noise in the signals. So these signals has to be carefully addressed when we carefully addressed in the pre-processing techniques. So here I have shown some of the noises. So for example, like the first one, the top signal, let's say, you have shown EEG signals, and this is actually this is corrupted by like EOG artifacts and ECG artifacts. We also like shown the clean ECG and clean EOG. EOG represents the electrical activity of eye movements, and ECG represents the electrical activity of heart functions. Okay, and here you see like EEG is contaminated by power line interferences after like having notch filters, like means after like means like after subjecting the signal to the notch filter, like we can remove the power line interferences. Then the resultant signal is shown. This is clean EEG without power line interferences. Okay. Now let me discuss about the complexities associated with physiological signals. So in this lecture, I would like to discuss about primarily about like EMG signals and then EEG signals. Let's say let me take EMG. EMG is nothing but the electrical activity of skeletal muscles. Yes. So if you look at the skeletal muscles, okay. Anyway, in a few minutes, I'll explain about the mechanism of signal generation. In general, like if you look at the skeletal muscles are made up of motor units, and then these motor units are made up of muscle fibers, and this muscle fibers has an anisotropic property. And this muscle fibers, if you look at like at a micro level, let's say not micro level, if we look at it at a nano level, nano scale, we can see that okay, these muscle fibers are arranged in layers, multiple layers, and it follows some non-uniform distributions. And obviously, these muscles okay respond to stimuli. Okay, and again, there are different combination of muscle fibers. So there are some intra and intracellular tissue variations. So the signals generated from such complex systems, okay, could be non-stationary. Non-stationary here we mean it. What actually we mean is the frequency components can vary with time. Okay, and it could be cyclostationary. Means this frequency components cyclically vary with time. Could be non-deterministic. Non-deterministic in the sense under ideal conditions we cannot get the same signals from the physiological from the human body. It could be anything from it could be ECG or it could be EMG or it could be EEG. We cannot replicate the signals. So there is intra variations and there is some there is intra-subject variations and there are also inter-subject variations. Intra-subject in the sense among subjects, intra is within subject. Okay. So this one. So the frequent. If you look at the biology, if you look at the biomedical signals, first the frequency and amplitude changes, then the frequency changes with time. Then there is upward changes, and there will be a subtle changes, and you can see sometimes the periodicity. Okay, particularly this periodicity represents abnormal phenomena. Okay, in whether like let it be in brains, okay, EEG, okay, or like let it be EMG. This when we are getting periodic signal from the biomedical system, let it be tissue, muscle tissue, or let it be a brain tissue. Okay, it represents an abnormal phenomenon. Okay, and even there are studies. It shows that these signals have a fractal behavior. That's what like higher dimension to lower dimension in the sense fractal dimension. So it has some fractal behavior as well. Okay. Now I'll discuss about muscular system. So muscular system. So we have, if you look at the human body, we have more than 60 muscles. Around actually 640 muscles. I think I'm to the means like I think I am correct. 60 around 60 means we have like around 640 muscles in the human body. It accounts about 40. These muscles helps us to perform fine and precise movements. Okay, and it helps us to maintain our posture, and it helps us for the communication. For example, facial muscles. Think about facial muscles. Facial muscles help us to communicate, right? No, facial muscles. Okay, so it helps us to communicate. In fact, now we are also working in facial muscles. Okay, we aim to means we are interested in seeing whether this EMG signals recorded from the facial muscles could be used for the control purpose. Okay, particularly because in tetraplegics means like persons, let's say those cannot who cannot use their upper and lower limbs. Okay, then the one available option is facial muscles. Okay, for the control purpose because they will be bedridden or if they want to use let's say wheelchair. So the facial muscles, because like the facial muscles, they have this thing, their facial muscles working properly. So like we thought that like we can utilize this signals and we see whether like can it be means will it be useful for those patients. It's like we are present we are working in this area. So and like generally these muscles, as I said, like it is made up of motor units, and these motor units again different types. Motor units is defined as one motor neuron and muscle fibers associated with. For example, you see just this is just cross section of muscle. Just it's a picture. It's not actual image. See, it's a cross section of muscle. Like we see like it has multiple motor units, and this motor unit have again like n number of muscle fibers and one motor neuron. So one motor neuron, okay, that actually this motor neuron connects this muscle with the spinal cord or with the central nervous system. Okay, so again the number of muscle fibers and number of motor units vary. For example, let's say thigh muscles. Okay, thigh muscles have large number of motor units, and the eye muscle, eye muscles are used to, for example, blink the eyes, right? No, so that like a very small number of whatever. So it depends again, like so as I said, like we have means we have different means like the number of motor units vary, and in fact like each motor unit have number of muscle units. So now we'll see about basic motor control mechanism. Okay, let's say just let's say we want to hold an object. Okay, we want to hold an object. Okay, so in this case ball. Okay, so basically see the moment we want to hold an object, like we see that, right? No, so we see that here the idea is how our central nervous system generates exact force to lift this object. Okay, so so the moment we see this the object, in this case ball, so this visual information has been sent to motor cortex. Then as we touch this ball, okay, then the sensory information again will be sent to the motor cortex. Now with this information, motor cortex generates I mean like recruits adequate number of motor units, okay, to generate the exact force for lifting this object. Okay, this is how like the motor control works. So this generation of exact force is a key mechanism. In fact, this is in fact like this is one of the issue in myoelectric control process, because let's say prosthetic hand, we don't have sensory information. So for example, like fine grips, okay, fine let's say like using prosthetic hand, like just we want to lift lift the this thing, like lift the this thing, like plastic water bottle. So so now since we don't have sensory information, it is difficult to generate exact force that is required to hold the bottle, because like if it is, because like if your system gives more force, let's say, then like it will crush, right? No, if the force is not adequate, then like obviously like the water bottle will fall down, right? No, so this motor control mechanism is very very essential, and like this is where like a lot of research has been happening in this thing myoelectric control field. So now as I said, like we have different types of motor units. Generally like this is classified into three types. Type 1, the slow twitch muscle fibers. It produces small force, and it is not easily fatigue. Okay, fatigue resistant. And if you look at the fiber diameter, it be smaller than the other types. So this diameter has direct connection with the conduction velocity. Okay, so when the diameter of the muscle fiber is smaller, then the conduction velocity will become lower. Okay, will be less. Then now you think about when we have signals. So when there is strong influence of slow twitch muscle fibers, then you can expect low frequency signals, because the conduction velocity is less. The velocity is directly proportional to your I mean like velocity is directly proportional to your frequency. Okay, it means like the velocity is less, then you have a low frequency signals. And then whereas in another case, let's say in type 2B, okay, it's a fast twitch, it generates a large force and it is easily fatigable. Okay, and the fiber diameter is larger, so it it just when means, so in this medium, the action potential propagates with higher conduction velocity, so the resultant signal will be with the high frequency components. Okay. For example, let's say power threads have a highest ratio of fast twitch fibers, and whereas endurance threads, for example, like slow runners, marathon distance runners, have a more slow twitch fibers. Okay, because like they have to run for a longer time, so we want more endurance time. Whereas in the earlier case, they want more fast twitch fibers. So like the ratio will be higher for them. So now what is muscle fatigue? Muscle fatigue is a neuromuscular condition which muscle fails to generate a rachial force. Okay, muscle fatigue. As I said, like, there are some conditions in which uh, muscle may not able to generate the rachial force. So the main objective of fatigue assessment is to provide early diagnosis of overtraining and muscle exhaustions. Particularly, this is one of the important reason why this analysis has been carried out in sports biomechanics. Okay, in general, it is normal physiological conditions and it is reversible. But this fatigue is a typical symptom for several neurological neuromuscular disorders. It has been reported that about 60% of patients often experience severe fatigue. Okay, 60% of neuromuscular patients often experience severe fatigue. Okay, so this fatigue plays a vital role in neuromuscular chemical analysis of neuromuscular disorders, and it is very useful in sports medicine and ergonomics and FES, functional electrical stimulation, and myoelectric control. In fact, myoelectric control, muscle fatigue is one of the very important factors to be concerned, because when we design a protocol, we have to ensure that the muscle that we are targeted, okay, should not get into fatigue state, because there is considerable change in the signal characteristics when the muscle is fatigued. Okay. So what are the method of analysis? Blood samples and biopsy. These are a conventional technique. Even like, for example, as I said, like, this neurological patients and neuromuscular patients, often they visit to hospital for let's say for the diagnosis. They usually prefer blood investigations and biopsy investigations. Okay, then conduction studies. So these three are invasive techniques, and then we also have some imaging techniques. Magnetic resonance imaging. It helps to it helps to identify affected muscles and damages, level of damages, and we also have ultrasound. These are like, costless techniques. So we have another technique called electromyography. It's the electrical activity of contracting muscles. Okay, electrical activity of contracting muscles. We'll see that this actually, it's a technique. As I said, like, it records the electrical activity of muscular contraction. So it is these signals are considered to be highly complex for the analysis, because many motor unit responses are superimposed in it. Here, see the shape of motor unit action potentials. Okay, the shape motor unit action potentials, and then the variations. Let's say we take EMG, the amplitude variations and frequency variations usually changes or reflects the neuromuscular conditions. For example, here we have shown the needle EMG signals. Needle EMG signals. See, this one is from normal muscle. Okay, and this one is from myopathy. Okay, myopathy is a disorder, like, it's a condition where, like, we don't have adequate muscle fibers, so we will not have motor and action potentials. So we expect that, like, the amplitude of the signals okay, should go down, right? So another case is neuropathy. Okay, it's a nerve disorder, so we will have like high frequency. So these signals, okay, these signals, okay, reflect the neuromuscular state up to some extent, but this is only for few cases. Whereas for there are some cases where we have to process the signal not to extract those information. Okay, so what are the types of I mean, like, what are the this thing, like, types of electrodes? So we have three different types. The first one is needle. The second one is surface electromyography. And third one is high density electromyography. Okay. So needle, surface, and HD EMG. Okay. Here, needle, needle, like, it is like, it will be directly inserted to the muscle fiber. So it has it will have a direct contact with muscle fiber. So it's and it is invasive. And since it has direct contact with muscle fibers, since it has a direct contact with muscle fibers, the SNR of the signal is high, and we will have better selectivity because you can aim the muscle fiber. Okay, you can aim the muscle fiber, so we have better selectivity. And this is how it's being widely used for clinical analysis. Okay, the results will be reliable, and we will not have crosstalks from other muscles because it is very localized. But this technique cannot be translated to, let's say, sports medicine or myalgic control, or let's say sports medicine, or let's say ergonomics. Okay, because this investigation can be only done by medical practitioners, doctors. Okay? This cannot be done by engineers because there are some rules and standards that doctors has to follow in order to get these signals. Then since this is invasive and we cannot translate this technique, or we cannot use this technique for the real-time applications. Then we have another technique, surface EMG. It's a signal acquired from the by placing the electrodes on the surface of muscles. Okay, it is non-invasive. It is non-invasive, and it is not that selective. By the way, it provides gross information about muscle functions. Okay, it is not that selective because we are going to place the electrodes over the skin. So we place the electrodes over the skin. So it is not that selective. It provides a gross measurement. Okay, but it can be used for several real-time applications. Okay, but so since for example, this EMG, we also have crosstalks. Okay, crosstalks in the sense for example, in this case we have applied means you can see the electrodes are placed on biceps brachii, particularly let's say scenarios like hand muscles. Okay, there are very small muscles in our hand. We have around around 20 plus muscles in our hand. So whenever let's say whenever we are interested in measuring, means recording signals from hand muscle, okay, these muscles are overlapped. So we will not get only the signals from the indented muscle, we also get signals from other muscles. Okay, so that's what we mean by crosstalk. Okay, crosstalk in the sense this is again one of the artifacts. Okay? So for that the signal has to be processed with utmost care. Then the advancement of this technique is high density surface electromyography. So it's nothing but this is again surface electrodes, but the diameter of this electrodes are smaller than surface EMG. Okay, and slightly higher than the needle EMG. You can see that, but here we have since we have multiple electrodes. Okay, and it's array electrode right now. So we have multiple electrodes placed together. So it will give better picture than surface electromyography. This SNR will be slightly higher than this surface EMG. Okay, we'll get large data. Okay, but there will be little crosstalk, and this is now being used in research purpose. So most of the applications we prefer surface electromyography technique. So this is just to give an overview of the different the different techniques. For example, conventional the SEMG, okay, it gives information about movements and it gives information about muscle contractions. It will not be going to give information about in terms of motor unit action potentials. Okay, and this HDMG, it's a one level advancement of surface electrodes. It provides additional information. It provides information about motor unit action potential because we have a lot of electrodes placed over the muscle, so we'll get more information, and from that you can extract. We can talk up to some level about the motor unit action potentials. Then this needle electrode, as I said, it is very localized. We'll get information about muscle fibers. We get a localized information. Here we see that the signals record from needle electrode. It's very clear signals right now. See, this is healthy, and this is a patient with neuropathy, and this is patient with myopathy, and this is high density surface EMG, and now this is the surface EMG. you see, like, no, the signal appears like noise. Okay, so we have to, but however, like, it has some valuable information in it. Like, so we have to select appropriate signal processing techniques and tools to extract those useful information. Okay. So in general, the surface EMG, if you consider surface EMG, the SNR of the signal is poor or low, let's say, because of its poor muscle selectivity. And then the characteristics of the signal depends on various physiological parameters. For example, like, as I said, like, the number of motor units being recruited or involved in the contraction. And then see how many motor units are first of all recruited, and how many times those motor units are recruited. Both actually, like, both actually this information develops manifests in terms of surface abnormalities. Okay, and then muscle fiber conduction velocity, and then number of slow or fast twitch muscle fibers are participated, and then volume conductor. Of course, like, we have muscle, then after that we have fat layer, and after that we have a skin. So the signal generated in the muscle has to travel all the way from means all the way through like, fat layer and skin layer, and then, like, we also have an interface, like, skin and electrode interface. So those things again, like, add some complexity in the analysis. So we have assessed the fatigue conditions in two conditions, fatigue conditions in two different contractions, let's say isometric contraction and dynamic contraction. Isometric contraction is widely preferred for muscle strengthening, and it's a contraction which the length of the muscle does not change. So it yields constant force. Okay. In another case, dynamic contraction, it's a muscle contraction in which the the length of the muscle change. Means, like, the force will be varying. And in fact, like, for example, let's say this all real-time activities, okay, will are associated with dynamic contractions. For example, let's say whether, like, will be walking or running. Okay, those activities we can directly relate with dynamic contractions. Okay, then, so in general, because of these factors, we say these signals are stochastic and multi-component and non-stress. Multi-component in the sense, at a time instant we will have, like, more than one frequencies. Okay, that's what, like, we refer multi-component. Okay, we mean multi-component. Okay, so in dynamic contraction, since it reflects the real-time muscle activities, the signals are considered to be more complex because the continuous changes in the muscle length and arms, and then, like, force, and then of course the movement of innervation zone. Innervation zone here, innervation zone means, like, see the razor means, like, we have motor neuron. Okay, this motor neuron connects to spinal cord, and the spinal cord connects to the brain, right? No? So this innervation zone are, like, called as neuromuscular zones. Means, like, where the motor neuron, okay, connect with your muscle. So for our work, we have taken biceps brachii muscle, and biceps brachii muscle. We have shown this. This is biceps brachii muscle, and we have followed CNM standards. See, in EEG, we have we have some standards for the electrode placement. One such example is 1020. 1020 is a standard. Okay, standard, international standard. Okay, but we don't have any standard for surface for surface electron SEMG recording. Okay, recently a group from Europe, okay, came up with certain certain means, like, they have done some procedures. Okay. This is like surface electromyography. This is a project of CNM, means, like, surface electromyography for the non-invasive measurement of muscles. So they have given like, some information. Let's say they have given they have given some recommendations for the electrode placement. So we have followed that, and then, like, we have used the AGAGCL type described the surface electrode, and then, like, we placed, okay, as per the instructions. Okay, instructions are given by CNM. We have placed the electrodes over the belly of muscle, and we maintain 3 centimeter distance, and we place the reference at the proximal end. Okay, and this is FDA approved biopack 36 database. So we have record signals in isometric fatiguing contractions and dynamic fatiguing contractions. For isometric exercise, there are 30 subjects 30 subjects have involved, and for dynamic 50 are involved. Okay, and then the patient demographics are given here, and we have chosen subjects, uh, those who have no history of neurological and neuromuscular disorders, and they are untrained people. Okay, so we have taken just no, we have taken from the healthy population, but they are not trained, and they are not trained, they are untrained, and they don't have any disorders. Okay, and we have explained our experimental protocol well in advance, and we also got an informed consent from them. We asked them to take 12 hours rest before the experiment. We have prepared the skin, and we place the electrode over the belly of the muscle. So now, the signal acquisition protocol of isometric contraction is given here. We ask subjects to stand erect on the internal platform for electrical isolation. And here, the participant's dominant upper arm is held in a vertical position close to body. This is dominant upper arm, okay, close to body, and then forearm in supine position, okay, so supination position, parallel to the ground, okay. Then this angle, elbow angle, is monitored using chart goniometer. Now we have given 6 kg dumbbell weight to the participant at 90-degree elbow angle, and we are asked them to maintain the angle. So participants stopped the experiment when the elbow angle is dropped by 10 degrees, or the subject is able to continue the exercise, whichever is earlier. Okay. So now we have seen the signals. These are signals recorded from the isometric analysis. In 4 cases, okay, in general, as far as fatigue results is concerned, first few seconds, okay, of the signal are considered as non-fatigue conditions, and then last few seconds of signals are considered as fatigue conditions. So we saw that the endurance time of the signals vary. Okay, and also endurance time, there is a considerable variation in the endurance time, and then there is a considerable variation in the amplitude. Okay, amplitude, and also there is a considerable variation in the oscillatory patterns. For example, here you see here we are seeing a lot of oscillations, whereas here you are not seeing such oscillation patterns. Okay, so it has some inter and intra-subject variations. Okay, and in dynamic case, we ask them to perform biceps curl exercise. Okay, we have given 6 kg dumbbell load, and here we ask the subject to perform continuous flexion and extension exercise until they are unable to lift the load and continue the exercise. Okay, see here we have given one single curve. Okay, one single curve. See, this is just flexion, and then this is extension. So during flexion we will get a burst. Okay, during this part is flexion, then this is extension, flexion and extension. So the signals of 4 subjects are given here. Here, so we see all these 4 signals. Okay, if you look at the endurance time is different, then amplitude is different, and as I said, the first few seconds of signals are recorded from the fresh muscles, right? No, because the first few seconds we are the signal means the muscle is fresh, right? No, and means at the end, okay, at the endurance time, the muscle is fatigued, right? No? So the first few seconds we just consider as non-fatigue, and the last few seconds are considered as fatigue. In that case, you see this 3 case, okay, see the amplitude increases, okay, during the progression of muscle fatigue, whereas in this case the amplitude decreases. Okay, for example, the conventional features, okay, the conventional features for the fatigue assessments are root mean square value, RMS value. Even in myotic control research, in myotic control, okay, they use RMS value, okay, to determine whether the muscle is fatigued or not. Okay, now in this case we cannot use RMS value because it yields contradictory results, right? No? So since as I said, this surface electromyography signals are non-stationary, means when the frequency components varies with time, we thought of identifying some high resolution type frequency techniques, not to see how the frequency components varies with respect to time during the progression of muscle.